and it will be by then the highest in Africa, the tallest building in Africa. Companies aboard the project, we have the main consultant, Al-Handasah, structural engineering, Al-Handasah, the peer reviewer, T.Y. Lin, San Francisco, the architecture advisor and signature architect is Perkins plus Wills. Main contractor is CSEC, China State Construction Engineering Corporation Limited, and the owner is the New Urban Communities Authority. The intention, the architecture intent of this is to be the landmark and the focal point of the project, and it's inspired by the obelisk of Luxor as in terms of looks. The exterior of the tower will be unitized painted aluminum curtain wall system with insulated very low Eve vision glass and continuous horizontal sunscreens. Some numbers. The total height will be 385.8 meters. The built-up area of the tower is 146,000 square meters, with a total built-up area of 241,000 square meters, inclusive of the podium. We have two outrigger floors. We'll get back to the number of outrigger floors when we talk about the seismicity. And the period after optimizing the design is 9.4 seconds. The design was completed in accordance with the Egyptian Code of Practice, and we opted to the use of some other codes after clearance with HBRC, being the authority that grants such clearances. Quantities, the foundation thickness is 5 meters. It's a raft, complete raft, 5 meters, not on piles, just raft. The total steel structure steel tonnage is 18,000 tons. The concrete volume is 225,000 cubic meters with the reinforcement tonnage of 35,000 tons. For the use of the tower, it comprises 77 floors. We have some color legend, but it's not very clear to differentiate between the different usage of floors. 34 offices, 34 floors of offices, 6 serviced apartment floors, 20 floors hotel guest rooms, 1 observation deck, upper and lower ground floors for the entrances and lobbies of the hotel, floors for the MEP, service hotel and service apartments sky lobby floors in the top part of the building, lower ground floors for the ballrooms and business center, and major services including loading dock and back of the house and MEP spaces. The structure system, as we can summarize it, it comprises central set of shear walls and peripheral columns. The columns at the periphery are a total of 16 columns. They are concrete filled steel tubes. The concrete filled steel tubes are rigidly connected, or fixed at base, and framed laterally to the shear wall system. The floor deck is composite deck on concrete on metal deck, compositely acting with the floor beams, and the typical steel beam connection with the cores are hinged. So the radial beams, as we see in plan, are framed to the steel columns and hinged to the central shear wall system. The lateral stability of this tower is ensured by the combination of the shear walls at the center and the columns at the periphery. The shear walls are interconnected together using a combination of coupling beams, steel coupling beams, and steel bracings. And we do have 2 floors of outriggers, one at floor 49 and one at 73. Moment resisting or moment connected at the cores and the columns so as to ensure the integration between the external skin and the central core system. These are some dimensions about the structural sizes. We have the columns varying from 1.6 meter and tapering up to 1 meter. We have the radial beams or the floor beams varying between a minimum of 300 millimeters thick and 650. At different floors they vary, but they all range in between 40 and 60 centimeter depth. The concrete beam depth, the green ones, are varying between a meter and 1.6 meter, and the thickness of the concrete walls also between 60 and 80 centimeters. On top of the tower there is this crown, whereby we do have some architecturally exposed tubular construction, and the sizes of the elements as per the legend. The columns again are 750, and they are not filled with concrete, by the way. These are empty columns or hollow ones, and the tubes that are framing columns are 30 to 60 centimeters. These dimensions are always dictated or limited by the architect. We might have worked it out with smaller sizes, but in here they had their own viewpoint. This is the steel bracing interconnecting the concrete cores. As I said, we had a combination of coupling beams and bracings. These are the coupling beams whereby we embedded steel sections into a concrete encasement and had their anchorage ensured in the walls by these vertical stubs to be able to transfer the shear. We had many challenges in this project, and maybe it's denoted iconic in terms of its function and height from perspective of the media and the use, but to us as well in DAR or in the design group, it had a lot of challenges that made it iconic by itself. The speed of construction and the choice of construction material. Here we carried out an exercise of comparing steel to concrete cost for the columns as alternatives, and the demarcation between the cost of steel and cost of concrete was not very much clear. I mean, if only the construction cost is considered, we might have opted to some concrete columns and local steel, not everywhere steel columns, but the construction speed that will be translated into revenue if the building is completed fast invited the choice of the steel columns as the alternative that the contractor also preferred due to their capacities and capabilities. So the acceleration of the construction had its input in choosing the structural material. The drift control as well was a challenge, whereby we started the design by only opting to the Egyptian code, and as such we had to have 4 outrigger levels to control the drift. We had a discussion and we had a research, then we had a discussion with the HBRC whereby we could secure their approval on opting to calculation of the seismicity according to the IBC, and as such we could relax the forces and satisfy the draft limit with only 2 outrigger systems. The outrigger construction by itself is very complicated, as we will be seeing in some of the slides, and reducing the number of outriggers from 4 to 2 does not only save on the steel quantities, but it saves a lot on the construction cost, construction time, sorry. For the wind analysis, we tested a rigid model at RWDI Ontario, and this is a photo of the physical model that has been tested. If you look at the share of the gravity loads and lateral loads in between the peripheral steel columns and the central core, the core takes 73% of the gravity loads and the peripheral columns take 27%, while the lateral loads, mostly as shear, are taken by central core with a minimal of marginal value of 9% for the columns, but the overturning is almost 50-50. So it's 60% by the core and 40% by the columns, and thanks to the outriggers that engaged the external skin with the internal core system. This is the drift per the latest seismic calculation, and as we can see, the controlling drift is the wind, not the earthquake drift anymore. Second, another challenge was the adherence to the architecture space. The architects in this project calculated or designed the space following the market pricing of square meter of guest rooms for the hotel. And as such, they were very stringent about the structural sizes. We had to use 80 megapascal concrete, and locally at some floors we jumped to Q420 steel, which is not locally produced. And as such, the tubular columns of this grade and some other parts of the columns were ordered or shipped, fabricated from China. The outriggers as well, the dimensions of it were very squeezed and limited, and as such we used this high-grade steel Q420 for the outrigger system. As another challenge, and this is actually, to me, this is why it is iconic. We opted in the design of this project, unlike other projects whereby the communication between the architecture product and the multidisciplines happen by exchanging Revit model or AutoCAD model and using it as a base for the structure, electromechanical, etc. In here, we opted to another scheme or another approach, whereby with the dynamic changes with our signature architect located in Chicago and development team of the architecture in Cairo, some trades are happening or are being designed out of Cairo office. So we had to have a 3D modeling algorithm whereby we utilize the Dynamo tool to interconnect the numerical model, the architecture numerical model, to the analysis programs, whether SAP, ETAPS, or STAT, to the Revit drafting tool. And with this tool, we could cope with very dynamic changes of the architecture and nice surprises of removing columns, shifting beams, squeezing heights, etc. So with this dynamic tool of Dynamo, that is a parameterization of the numerical model coupled with a genetic algorithm. Its terminology is biological. So it could satisfy the purpose of dynamic changes and reflection of the architecture changes to the structural modeling of the analysis to the Revit structure product, and vice versa. Whenever we change something on the analysis, some sizes on the analysis models, it reflects on backward to the Revit, and everybody can see it including the architects, and they could see that some members could not satisfy their limitation and had to be increased, etc. So this automation enabled us to cope with, as I said, with the dynamic changes and with the fact that we are not stationed in the same center, and it also allowed sort of quality control on the analysis models and making sure that the drafting is automatically reflecting the outcome of the analysis. There is no room for mistake of denoting a member size in the drafting or in the product drawing that does not match the analysis. It doesn't have a human input at the first hand. It just reads the outcome of the analysis and reflects it on the Revit modeling. And it also allowed for ease of calculation of the quantities and for considering exact length of members so as to avoid the duplication of the member intersections at the joints in calculating the quantities. In the analysis, we also considered the construction stage analysis. So we had to, or we were able to run the time-dependent properties of concrete in terms of creep and shrinkage, and to see or to build models, different models for the different construction phases, so as to make sure that what the outriggers and external columns will suffer from along the construction phase is covering the full spectrum of the service condition and the construction condition as well. As for the connections, that was another challenge. It's built in, and every steel designer's background, especially in this part of the world, that bolted connections are the first option, and that welding and the quality control of it is always happening at shop, and all site connections are done by bolting. We were requested by CSAC, the contractor, to opt to welding with full attendance of third-party quality control at all heights. I mean, all the connections of this project were done welded, site welded. And we, for this, we also studied the conditions of temporary lifting, and we had these red plates as temporary plates until the full welding takes place. This is a simulation of one of the connections, typical floor beam to the columns, whereby we had, if we get back to the model, the column does not only receive radial beams, it has radial beams as skewed ones and the peripheral ring ones as well. So the connection we opted to use was having two flanges at the deepest section of the beam and receiving the radial, peripheral and skewed one to these brackets and applying along this side, this edge, a full controlled site welding. And this is another sample for the outrigger, whereby we had the outrigger elements formed out of boxes, and as we can see, this is but a single joint of receiving the outrigger cords at the column, and this is another proof of how much the dynamo tool we used, that started by the numerical model and drawing the center line, could serve the purpose of presenting this Revit drafting output and also supplying the analysis with this exact intersection detail for the finite element to be run truly on the true geometry. And this is a sample of the finite element models of the pin details of the ties with the main beams at the entrance canopy. The fire resistance. For this project, we had a clear instruction according to the code, the local regulations, as well as the NFPA. We have to have the vertical elements as well as the outriggers 4 hours fire resistant. Ensuring 4 hours is not very simple, because actually most of the space here is delivered as core and shell, and as such the tenants or the vendors or whoever will use the space will receive it unfinished, except for the hotel. Only the hotel will be finished, but otherwise all the areas of these 77 stories minus 20 and 57 stories will be unfinished, and as such having to have 4 hours fire rating for an unfinished product means opting to intumescent paint. Intumescent paint does not ensure 4 hours. We did our research worldwide and could receive some quotations and promises that ended up untrue, and the only one that could promise to provide such material, though couldn't prove viability, cost $600 per square meter of steel surface. If we calculate the surface area of the 18,000 tons, that means we would have paid $13.3 million to fire protect the columns and outriggers. And this is totally irrational. And yet, we're not sure if doable, regardless of the cost. So the cementitious material was the option, but the challenge here that the cementitious material is not fair-faced. It looks like shotcreting, and it has to be concealed as well, because it's very sensitive to humidity, until we could research a product that can or promised this, and we made a mock-up of it. This is a cementitious, fair-faced fire protection that we ended up using. And as we can see, the cost comparison, it costs only $120, and as such, its cost over the 18,000 tons does not exceed $2.6 million. During this phase, we had a sort of disagreement or debate with the contractor. They said, we have the concrete filled with, the column is filled with concrete, and as such the humidity of the concrete can help reducing the temperature of the steel surface. And we said yes. In 1993, we used this technique in Beirut International Airport, but with flowable concrete, with high water content. And here we do have 80 megapascal concrete with very limited water content, and as such, its ability to cool down or to heat sink the temperature of the steel surface is not as efficient. They tried to prove the point, and we were open to analyze it. And they did thermal analysis using the ANSYS, whereby they simulated the column and concrete filling with its true properties. And from the ISO 834, the steel starts losing great portion of its yield and elasticity modulus at almost a temperature of 411 degrees. So they run a model whereby they engulf the column all around with heat, simulating a theoretical fire condition. And in their analysis, they see, I'm sorry, the numbers are garbled. In here, the temperature reached 1,000 degrees. In here, with 5 millimeter of fire protection. So they started applying the dual system. I mean, using here the upper one is unprotected column, just concrete filled. The one below is concrete filled with 5 millimeter of intumescent material, theoretical intumescent material, and still the temperature reached 639 or 619. They did another one and increased the thickness of the external fire protection to 1 centimeter, and still the temperature was 500 degrees. Our argument here was not only the concrete ability to cool the steel. The argument, even if the concrete is having a high water content and flowable and whatever, the problem here with the dual system was that the concrete will start doing its action while the intumescent is trying to protect the steel. So the fire is from outside, the intumescent paint is swelling to protect the steel from melting, but the steel is still getting hot. As the steel is getting hot, it engages the concrete filling to start cooling it timely or simultaneously with the effect of intumescent paint. So their idea about ensuring 2 hours fire protection by external painting, then another 2 hours by the concrete filling, was not very correct conceptually, regardless of the concrete ability to do it. Because the concrete will act in the same time with the steel. So it's not an algebraic summation between 2 hours plus 2 hours. We, instead of this, after reaching here, it was very clear and evident that 5 millimeters of intumescent or 10 millimeters of intumescent that doesn't exist would not, or actually here they were talking about intumescent of 2 hours, so it exists. So this is a low-class intumescent paint that only ensures 2 hours, and it's available. It's at cost, but it's available. But it didn't work because the temperature exceeded the 411. So we engaged our CFD specialist to simulate the case differently. Instead of engulfing the column with an all-around fire for complete 4 hours, he followed a fire scenario whereby local area of the mechanical floor will be subject to fueled fire to induce 4 megawatt fire event. He simulated it to happen at 80 centimeters from the column, from one side, a 2 fire condition, and let it spread with time. With the CFD, so he had here the column, composite column, were modeled with as hollow steel plus concrete filling with the true water cement ratio of 0.25 and simulated only 4 floors around the fire. The chart here shows that the increase in the temperature of the outer surface of the steel that is not protected only with the concrete filling slowed down after 2.5 hours. It gets hot quickly along the first 150 minutes, then it's slowing down, its increase of temperature is slowing down, and after 4 hours it reached 300 degrees. In fact, we did this study despite the fact that we are protecting the columns with the fair-faced, good-looking cementitious material as a second line of defense in case, with time, in case the tenants did not get in quickly to use the space, in case some floors are not occupied for some years, and the cementitious spraying is losing characteristics because it was not concealed. So what will happen? Will it get? I mean, will it collapse in case of fire? No. The answer with this study proves that with the low water content concrete filling, the steel surface under a true fire scenario would not reach 411 degrees after 4 hours. And as such, This is another line of defense, but definitely it's uncodified. So this study is meant to be to clear our mind from the worries, but we didn't use it in the final product. The final product is cementitious sprayed to ensure 4 hours with a total negligence of the concrete filling, and here the concrete filling is more than enough for the protection, and as such we have it duplicated. The fire protection here is ensured by 2 lines of defense. So these are the main differences between what the contractor tried to do with the ANSYS and the CFD, as I just highlighted. Some local architecturally exposed elements had to be subject to intumescent paint, and they wanted to play with the colors as well. And thanks God, these architecturally exposed elements per the code are 2 hours fire rated, and as such, intumescent paint could do for them. Here we do have some photos of the construction. They recorded the concrete casting operation to be the fastest in Africa and the Middle East in March 2019. Now we are at 52 meter high of the core, and almost 14 meters of the column are installed. In December, we moved from 52 meter high of the core, we reached 80. And this is still I was at the site last week, and this is the exact condition, but all the radial beams are now connected of the 16 columns. Thank you.
Thank you, Dr. Sameh, for this very interesting presentation. And now we go for some questions.
Thank you for your nice presentation. And I have some questions regarding the progressive collapse. Progressive collapse. Have you taken into consideration the progressive collapse scenario? I have seen that you have considered the fire scenario, but for such abnormal load like glass explosion, the behavioral structure, the response structure with the progressive collapse in glass is totally different. You could find something like so the responsive structure, resistant structure for glass elements is totally different to fire. And most of the international codes noted that you have to take into account removal scenario for some columns regarding to progressive collapse in case of such abnormal load like impact load, high impact load, or blast load. Have you taken into consideration?
We consider column removal, but blast is a different story.
Yeah,
I mean,
that's
it's
why
by definition and by code, by local regulations, we are not supposed to design this building against blast. What power of blast?
Power of blast?
Yes. What's the size of blast?
Maybe blast will do some internal blast for the surface area. Blast may be occur for many reasons. Maybe happen due to some terrorist attack from outside, and also maybe it happened internally due to some in the surface area, some explosion, gas explosion inside. And that all international groups they have mentioned that we have to take into account the progressive collapse due to blast.
Definitely, we took a progressive collapse condition by removing one of the columns with its radial beam. But the blast has another effect. I mean, the explosion itself might not be, its damage might not be limited to cutting off a single column.
Yeah.
So, but we are following the regulations by considering a single column removal with its connecting beam or beams.
Which floor? The ground floor or the
In all if I'm not mistaken, we considered a case in 2 consecutive floors as well.
Yeah. Thank you.
Thank you.
Thank you for this presentation. Shair. I have a lot of questions concerning the steel structure. First of all, why you use infinite columns? Why you don't use infinite columns? It's going to solve the problem of fire, the problem of connections, all the problems which you inherit here is going to save a lot of it. Second thing, why we use welding connection. Welding connection is going to take time, and you have a problem with time. Also, it's going the quality control of it is going to be very difficult. Also, how are you going to make slides? Columns. You have every 24 meters or 12 meters, you have a splice. So how are you going to do it? So basically, I'm going to remember.
So our preference from the very beginning, and actually if I get back to another project that we've done like 10 years ago, it's Dubai International Airport. The cruciform embedded in concrete is the optimum structural configuration for this column. The most optimum is to make it cruciform of I-beams embedded in concrete. We did a study about this in the old days, and we repeated it here. The difference in diameter between the safe section of tubular CFT and the encased cruciform is 8 to 10 centimeters. I mean, this is smaller by 8 to 10 centimeters. And we had a very stringent argument. And the argument that was always ready to defeat all these rationalization approaches was that the space is sold in square meters. And if you pay more for the steel construction cost, we are saving millions for the reduction of the column size, and as such gaining more time, more money for the area. So it was put on table and discussed openly that the tubular column is the smallest in size, but the complex in construction and the unit rate of it is the higher, by the way, in terms of steel material. So this is why we didn't feel free, or we were not given freedom to do the optimum structural thing. Second question was about the site welding. As I said, all our connections until this 30% completion or 40% completion progress was bolted. CSEC is a Chinese contractor that is more well versed with welding. They came with a very fat database about their projects under different consultants in the States and in China, whereby they could satisfy the quality control of welding. So we talked about regardless of the quality control, it takes more time. So surprisingly, they said no. It doesn't take more time because the alignment and the misalignment and misfitting of the bolts at this height might necessitate doing a lot of touch-up or adjustment on top. Whereas the welding is shipped cut to length, shipped from the fabrication, cut to length with the beveling and chamfering happening at shop, and they only do the welding on site. So the challenge will be the third party, to have suicidal third party that will be climbing with this height.
Okay, thank you. Now for more questions. Please.
First of all, you will build on some assumption, okay, about the location of the fire source. In my opinion, you have to make two trials in case of the direction of direction. Okay. Or the second option would be radial, okay. The first option is the direction of fire will be upward. Okay. Second one will be in radial. So you can make your calculation according to the rise in temperature for the speed column. This is one. Your assumption depending on the location of fire source. What about the propagation of fire? So the test must be done according to the standard, and you have to achieve the 4 minutes for the worst case, not on the assumption for the true action.
Yeah.
Second one, second question. What about the space around the columns? Because when you decide to use a constant paint, you have to allow some space to expand. Okay? So, in this case, why you cannot use the cementitious one? If you have the space, is it only for the load, for the extra weight? That's it.
I will answer backward. The issue with the cementitious was again the squeezing of architects with respect to size. They accepted 1 centimeter of intumescent and was very stubborn to accept the 4 centimeters of cementitious. So they ended up accepting it. I mean, but the argument at the beginning was because of this. So we do have an offset, a clear 40 centimeters, if I'm not mistaken, between the inner of the curtain wall and the external surface of the column. So before installing the curtain wall, we have space, and we can apply the cementitious, but the debate or the bargain approach was about the 4 centimeter extra that the architects were stubborn to accept. Now they did. As for the fire propagation, we acknowledge that in case we were to legitimize the study as a proof that we will not do fire protection because we simulated every scenario, we should have done this. But actually, it was only a case to argue or to counter reply the contractor's claim that an all-around like flame or torch directed to the surface of the column is a simulation. This is wrong. So we did one rational probability of fire, but it is not every probability, definitely. And if it was to be justifying not protecting the columns, we were to do all the, but we stopped there because actually we applied the 4 hours cementitious. So we do have the 4 hours cementitious plus the concrete filling.